So my name is Steinmetz. I'm leading the worldwide business team for HEV, EV, and Powertrain systems. I'm based out of Germany, and pleasure for me today to walk you through this press announcement. So what we are talking about today, accurate monitoring and protection drive HEV and EV farther and longer. So what does that basically mean for the end customer, for the driver? Having a larger mileage from a single charge and spend less time at the charging station. So this is the overall goal, and obviously we want to all do that in a safe way. So from the agenda, I will run you through the short overview, the road to electrification, the way how TI looks at the automotive market when it comes to HEV, EV, how does hybrid electric powertrain system look like today, and from there looking into the new Part 3 announced today, so reference designs and of course products in the range of battery management, temperature management, as well as gate drivers. So TI is a long-lasting supplier in the automotive market. We play in all the 5 major areas, starting here on the left, advanced driver assistance systems, so advanced assistant autonomous driving capabilities to compensate and assist, so compensate for human errors or reducing them, and assisting humans while driving. These are things like lane assist, adaptive cruise control, and so on. The other one, passive safety systems, probably not that known to the broader audience. TI is active in there as one of the key suppliers since the 80s of the last century. So we're talking about braking, airbag, tire pressure measurement systems. Third one in the middle, body electronics and lighting. So here we're talking about comfort functions inside the car, gateways, as well as interior and exterior lighting from the different technologies. Then the next point, infotainment and cluster, means from the car audio to premium audio to the cluster to the fully digital cluster head-up displays. These are the kind of applications which are under infotainment and cluster. And finally, my area, hybrid electric and powertrain systems. This is all about reducing emissions by electrification. So being compliant to worldwide government regulations on reducing emissions, mainly CO2 emissions, but as well other toxic gases like NOx and soot, and so on. So there is a road, how we call it, the road to zero emission. So today, most cars, or the vast majority of cars, is using an ICE, so an internal combustion engine. And when we talk about start-stop systems, some automotive manufacturers already call that being a micro hybrid. So these are 12-volt systems. These are, typo, less than 5 kilowatt, not that 5 watt, obviously. When you talk about savings, this is around, we're talking about CO2 savings, so emission savings. This is around 3 to 10%, always depending on how the car manufacturer is finally building its product, all 12-volt systems. The end equipment you have here, so the inverter motor control, the starter generator, is the technical equipment you use to do a micro hybrid. The next step up the ladder in terms of electrification is the mild hybrid, predominantly 48 volt, some high voltage, but 48 volt seems to be the sweet spot. And here we're talking about 5 to 12, in the meantime up to 40 kilowatt of power out of the 48 volt line, 8 to up to 30% of CO2 savings, and what you have in here is an inverter, a DC-DC converter, and obviously a battery management. A 48 volt lithium-ion battery is normally used in these kind of systems. So what can it do? You can downsize the combustion engine. You have an electric torque assist by over-dimension starter generator or real traction motor, and as well other electrical loads can be used, like electric pumps, like electric turbocharger instead of an exhaust gas driven turbocharger. So all that helps to improve the overall efficiency. The next step up is the full hybrid, and the full hybrid predominantly uses high voltage, and it allows an electric only drive mode. This is an area, these were probably the first hybrids in the market. If you add an onboard charger to a full hybrid, you end up in a plug-in hybrid. So what does that mean? It can be recharged, the battery can be recharged from the grid, which means the pure electrical mileage is just limited by the size of the battery, by the capacity of the battery, and the time you spend while charging the battery at the charging pile. The saving potential is quite impressive. 40 to 80% savings are possible, so that is clearly as well one of the intermediate vehicle types we see successful in the market. Finally, then we have the battery electric vehicle, so pure electric vehicle, clearly 100% of CO2 savings, so no local emissions, and the battery size is obviously the most important thing to get the appropriate mileage out there. Normally much larger from the power level, much larger than 50 kilowatt. So there are relatively low number of entry-level cars. 100 kilowatt plus is what we see as a sweet spot in the market. And these two are probably the most important ones these days, specifically looking into as well the Asian market. The one on the right side is far out in the future, but already today outlines the importance of high efficiency and power density. Just think about, you were able to add a solar roof, a solar active surface to the body of your car, as well as recuperating energy from shock and vibration by an active suspension. And this gives you, the technology available today probably allows you to increase the mileage of your car by 10%, or if you want to stay with a given mileage, reduce the size, the cost of the battery by 10% to end up with the given mileage. So this is quite an impressive optimization, and underlines why power efficiency, power density, as well as advanced monitoring is that important. To sum that up, I was looking again into the classification of vehicle electrification. Again, to remind you, this is all to reduce CO2 emissions and other toxic gases. So how to reduce overall emissions? There are basically three ways. The first one is improve the combustion engine. So improving the efficiency of a combustion engine, reducing the weight of the car, improving aerodynamics. These are all things which help with a traditional car. By offloading the combustion engine means adding electrical loads or replacing classic mechanical loads by electrical loads. This could be cooling fans, fuel pumps, water pumps, engine pumps, electric turbocharger, traction inverter. So that helps from the offloading perspective. And finally, the full electric drive in an electric vehicle or a plug-in in a full electric drive mode that reduces the local emissions by 100%. This is clearly the way where the industry is heading today. So by 25, major car OEMs worldwide are kind of forecasting around 30% of their entire production being electrical or electrified. So that, I think that is an impressive number given the speed of deployment as well. So now jumping into the area or the specific announcement for today, monitoring and protection. Again, driving HEV EVs farther and longer means, again, for the end customer, spending less time at the charging station and more mileage with a single charge from the battery. That's what it's all about. So the first part I'd like to introduce is actually a reference design. This reference design is a scalable automotive 6S to 96S battery cell supervision reference design. You find it on ti.com with that number, so TIDA 01537. You find all the data on the TI website, starting from schematic, Gerber files, user guide, test report, software if applicable. So it should help customers to jumpstart the development and reduce the overall time to market. So in other words, being able to react to the dynamic market needs I just explained in the earlier slides. So what does the part or the reference design is capable of doing? So it's a battery monitoring and protection from a 12 volt up to a 400 volt battery management system. So 6S to 96S, so up to 96 cells in series connection, end up in the 400 volt, and the 3 to 6 then in the 12 volt scenario, and obviously everything in between which customer might be needed. So the reference design supports a battery accuracy across all voltages, all battery voltages, talking about a stack, whether this is the 12 volt, the 48 volt, 400, or anything in between, with less than 1% of overall error on the cell voltage measurement. Very important point, the cell voltage measurement is a key factor, a key parameter to be measured. It needs to be accurate and it needs to be simultaneous measured. So which means if you have 96 cells in series, all these cells need to be measured at the same time to be able to have a meaningful understanding of the state of charge and state of health of the overall battery. This is the key factor which allows at the end the control unit to charge the car fast and get the maximum charge out of the car to drive. Footprint as well is of a major importance. So 20 by 40 millimeters for a single BQ79606A, so that is actually the part which is used in here. You see it 16 times on that board. 16 times 6, so up to 96S support. And each of these areas, so the small square here is the 20 by 40 millimeters, which is an important size, an important piece, as the battery management needs to be built in the battery module, which is space constrained. Finally, the design helps designers to support ACLD or up to an ACLD functional safety requirements. Functional safety, talking about batteries, an electric car in general, is an important topic. The industry is trending towards ASIL D, which is the highest level of functional safety standard defined by the ISO 26262. And our parts being used on this reference design have the Safety Eye trademark, which means they are designed in line with an ISO 26262 certified development process. So we help customers, we enable them to achieve the safety goals, but finally the final safety architecture and responsibility is on the customer side. So they have to run the certification, they have to do everything to the end to cross the finishing line, but we help them with the parts, with the feature set, with our development process to get there. So the part being used in that reference design is here the BQ79606Q1, so precision monitor with integrated hardware protector for EV drivetrains. So, and you have just a simplified view, simplified block diagram in here. So the BQ79606, it supports large battery stack configurations in electric drivetrains. So that actually is from up to 64 of these ICs can be connected in a daisy chain, which brings us from 3S, so from 3 cells in series, up to 378 in series, which allows everything from 12 volt, 48, 400, 800, probably even up to 1.5 kilovolt of a battery. So from the car trend, an electric car today, we see 400 volt being the sweet spot. Most electric cars today are in the range of 400 volt. Next generation performance cars are most likely going towards the higher voltage. We're talking about 800 for performance cars, and for public transportation, for buses, for electric trucks, it can go even higher, close to the kilovolt or slightly above. Again, I mentioned before the simultaneous accurate measurement of voltages. It's important. The second important measurement on the battery next to the voltage is the temperature. So a customer wants to make sure that he's in perfect control of the temperature of a battery, as lithium-ion batteries are critical to temperature at very low temperatures. It's difficult to get the energy out at high temperatures. At a given point, you have to cool them down to stay in a safe operation area, which means an accurate temperature measurement as well needs to be featured by these parts, and it's as well built in the BQ79606. So with an auxiliary A to D converter, we can connect up to 6 temperature sensors to each of the parts and monitor the cell temperature. Again, the point I made on the previous slide, it helps meeting ASIL D, so the highest functional safety goal for the ISO 26262 road vehicle standard. So how to achieve it? Just to resume here, the high precision voltage measurement, simultaneously the temperature measurement on top. We have as well the integrated protector. Protector means there are comparators built in which as well on its own detect whether there's an undervoltage or overvoltage condition. So an additional level of diagnostics which help customers to get a better understanding of the battery. And last but not least, a very important piece is the communication. So first off, it is isolated by capacitive isolation, which is a very simple and by that small and cost-effective way to do the isolation. And as you might imagine, if you have 16 or in a 400, in an 800 volt scenario, even 32 of these ICs connected. The isolation in between is quite an important thing because of the multiplier. So, and the other point is, you have the optional ring architecture. So you can see here, this is optional, the ring architecture, and that increases dramatically the capability of customers to build safe systems. So just imagine you have a broken cable in here, in between. With a ring architecture, the microcontroller can start a communication up here, up to that point, and cannot reach this part. But then he can start the communication from the other end, and still reaches all parts, means have a full understanding of the state of charge, state of health of the battery, plus being enabled to get the diagnostics, which means probably for, what does it mean for the car driver? So in one scenario without the ring architecture, and you have a broken cable, your car is standing still, probably on the left lane on the highway, and you have a dead car. That's scenario one. Scenario two, with our parts being released today, you still have a full understanding of the battery. The car is able to drive even with a failure. You can maintain the battery in a safe operation condition. The car owner can still drive. And there might be a red light in the dashboard and the cluster showing, please go to the maintenance station. So in other words, you enable by that the so-called limp home mode. So this part as well has an evaluation board, and the evaluation board is as well available now on ti.com for $199. Just to wrap up again, it has 6 channel per IC with integrated protector, includes the daisy chain communication port, and it's stackable up to 64 modules to support as well large stacks up to 1.5 kilovolt. So the next one, I talked about temperature before, and a highest accuracy precision temp sensor for EVs, the TMP235Q1, as well being announced today. In an electric car, there is kilowatts of power flowing through, let's say, a traction inverter or an onboard charger, even targeting highest efficiency, power efficiency. You probably have 1, 2, 3 kilowatt of power losses in the power stage. So whether this is IGBT, silicon carbide, or standard FET-based, there are power losses, and you want to monitor them. So traditionally, this was done with NTCs, which have some shortcomings, especially when it comes to high temperatures. So the tolerances of these were that high that, which at the end means you cannot provide appropriate control of your system at high temperatures. So with the TMP235Q1, we have a typical accuracy of plus minus 0.5 degrees C over the entire range, operating ambient temperature range from minus 40 to plus 150 degrees C, which means I can stretch now, taking the example of an onboard charger. I can stretch now the power delivery to the limit, charging the car, the battery faster, because I exactly know where I am. I do not need to shut down at 140 degree because of lack accuracy of my temperature measurement system. I can go to the 150 because I have the accuracy up to that level. That's an important point on how to optimize the overall system on the onboard charger that directly impacts charging time, on the traction inverter that impacts the performance while driving, whether that is available mileage, whether this is torque or driving performance. all the different parameters are directly impacted by a proper sensing of the temperature. And finally, the TMP235Q1 is the highest accuracy precision analog temperature sensor for these kind of systems being introduced today. So the next one is, as you might know, there is a strong trend in the industry as well to optimize the two major factors. One is power density, the other is the power efficiency, and the use of wide bandgap transistors like silicon carbide play a crucial role in this game to overall improve efficiency and the power density. So the UCC 21710Q1 is the first isolated gate driver with integrated sensing capabilities, which is optimized to be used with IGBTs as well as silicon carbide power switches. And by that we achieve advanced monitoring and protection while improving the total system efficiency in, as an example, traction inverters and onboard chargers. So we do that by enhanced system performance, strong system reliability, and reduced system size. Just to mention one or two examples on that. So the enhanced system performance, a high peak drive strength of plus minus 10 amp. This is very new to the market, having that integrated in one IC. Traditional gate drivers need to have a current booster, so external parts to drive large transistors, whether this is IGBT or silicon carbide. So it is external parts to make it difficult to control, time consuming and space consuming, and as well costly. So we have this power stage integrated, and that makes the design overall easier. At the same time, when you're using silicon carbide transistors and you increase the switching frequency, your protection needs to be much faster, so to protect the device, and therefore 200 nanoseconds of overcurrent detection enables a fast system protection, specifically of importance for silicon carbide. Another point is the strong system reliability, and specifically here the insulation barrier. So I talked about 400 volt, 800 volt trend to go even higher. That means this is a very critical and life-critical voltage. So the isolation technology being used is of a major importance. So TI has its industry-leading reinforced isolation and built in this part, which means you can use this part again up to a DC bus voltage of 1.5 kilovolt, a typical isolation voltage of 5.7 kilovolt, and the surge immunity up to 12.8 kilovolt. So very important point from the system reliability perspective as well, integrated in that one IC. And finally, the reduced system size. So there are external components, or the need of external components is eliminated by integrated buffers, sensors, as well as an integrated, isolated analog to pulse width modulation sensor. It can sense things like temperature of the power switch, voltages, as well as currents, and send them back across the isolation barrier to the microcontroller. So all in one IC. In the past, that was probably a larger piece of schematic with 4 or 5 parts, if not more. Excuse me. And again, we have here an evaluation board available on TI.com for $99. So just to reiterate the major points, 10 ampere peak split output drive current with programmable drive voltages, two 5.7 kilovolt RMS isolation channels, support up to 1.7 kilovolt of input voltage rail, and short circuit protection with soft turn off and Miller clamp with internal FET, as well all the specifics needed to control these power switches fast and reliable are included in this part. When we have a traction inverter, and what you can see here on the picture is an IGBT with a driving PCB, and the PCB you see on top is as well a reference design. Actually, it is this one, the TIDA 20014. This one features 3 different types of bias supplies for the gate driver. And why 3 different? Very easy. We have different, or each customer, each car manufacturer has a different architecture, and we want to enable our customers to easily select from one of the 3 what is the right architecture, the right solution for the given use case. And the second one, which is not on the picture, it is a 4.5 to 65 volt input bias supply, as well for IGBT and silicon carbide gate drivers. And that one specifically features one of our new parts now on this slide. So this is the LM5180Q1, 65 volt input primary side regulated flyback converter with an integrated 100 volt FET and 1.5 ampere current capability. So why is that part different to the market? So it has an input voltage from 4 volt to 65, which means it can be directly used and connected to the 12 volt battery in the car. And it can be as well used to connect to the 48 volt battery in the car. Which means, if you think about how a system is built, you have, for a power switch, you have a gate driver, and this gate driver needs to have an isolated bias supply. And this part now enables to generate this isolated bias supply directly from the 12 volt, so there is no intermediate voltage needed anymore, which means at the end there is one stage less, which is cost and space. But even more important, it is a reliability thing, because without having the need for an intermediate rail, there is from the safety architecture, there's a dramatic improvement in the overall architecture. On top, as said, this is a primary side regulated with the ultra low quiescent current, which is important if I want to connect something directly to the battery. The quiescent current is of a major importance. And as well, there is no optocoupler or transformer auxiliary winding needed, as it's primary side regulated. Again, this is space and this is cost of external components. Last but not least, this is as well complexity of the design. I started the presentation with the 2 major benefits for the end customer, the driver of an electric car. Again, having a maximum mileage from a single charge and spending a minimum time at the charging station recharging the car. So I think it makes sense to look quickly into the different charging stations. There are, let's say, 2 main types, and there are subtypes on it, but to stay on that level, one is the AC charging, and one is the fast DC charger. So the AC charger means, EVSE means electric vehicle service equipment, or another different word for the charging pile. The AC gets into the car, and on the car you have the so-called OBC, or onboard charger, which converts the AC into a DC voltage which follows the battery profile, and by that charging the battery. From the power levels and the voltages, this strongly depends on the regions, so worldwide regions. So, for example, in Europe we have a three-phase AC grid, or in Central Europe and South Europe it's just one phase. In the US it's one phase. So that strongly depends, and we see here 120 volt up to 240 volt, single up to 3 phases, and that ends up in around 1.5 kilowatt to 22 kilowatt of charging power. Obviously there are some niche implementation below and above, but this is kind of the sweet spot. That translates from electric car, depending again on the size of the battery, to 5 to 15 hours of recharging time, which is probably okay. Recharging the car overnight if you're on a long trip, probably spending 5 hours at the gas station, you would not accept. So that is exactly where the fast DC charger kicks in. So on the fast DC charger you have a charging pile which does the AC-DC converter and directly feeds in the DC to the car, bypassing the internal onboard charger, directly going to the battery pack. And these ones, we see very dynamic developments across the globe. So 300 volt to 1000 volt on the input, respectively output side, 400 amps currently being the maximum. That translates to 20 kilowatt to 350 kilowatt of charging power. Latest pilots show up to 450 kilowatt of charging power, and that then finally translates into a charging time. So the time you spend waiting for your car to drive again, 15 to 30 minutes to get it pumped up to 85 or 80% of the total capacity. And that is basically one of the key areas we at Texas Instruments as well focusing on, because to achieve all these numbers and to reduce that time, it's about power density, it's about power efficiency, and it's about accurate monitoring and protection. Just to look very briefly into what does it take for fast DC charging. So fast DC chargers normally are built up modular, means you have modules each being 10, 20 kilowatt, and you stack them to achieve the required charging power of, let's say, the 20 or 40 kilowatt to up to the 350 kilowatt. The energy density can be increased with faster switching speeds, and that ends up in system cost optimization. So faster switching speeds means if you change from standard transistors, from FET or IGBTs towards silicon carbide. Silicon carbide, due to the lack of reverse recovery losses, is you can switch much more efficient, which means this is one thing to get the power density and the efficiency to a better level. And secondly, if you switch at a higher frequency, the passives get smaller, so mainly the transformers and inductors can be dimensioned much smaller. So you increase dramatically the power density, and that is a huge system cost optimization. So here looking at the charging profile of a lithium-ion battery, so to get up to around 85% of a charge, you need to run with the current, constant current mode, and then you change over to get the rest charge in, or top-up charge, with a constant voltage. And that means you have to have as well a very accurate control on the current and the voltage side, with the high power being in place, with the monitoring, to have an accurate charging curve. So this charging curve, this charging profile of the battery, this has to be followed. Not following the charging profile is dramatically reducing the lifetime of the battery itself, up to a dramatic failure of the battery. Therefore, it is really important, the monitoring and protection as well, the accurate control is a key feature in the electric car and directly translate to the benefits of the end customer. The last reference design I'd like to introduce and show you is a three-phase silicon carbide-based reference design for the fast DC charging. This is a 10 kilowatt module. I said this is a modular approach. We built up a 10 kilowatt module with up to 800 volt of DC output and a peak efficiency larger than 89%. Still, if you do the math, you still have 200 watt of power losses. And just remember the temperature sensing I talked before, 200 watt of power losses on in a relatively small condensed end equipment is quite a lot, even with the highest possible power density these days. So this is a three-phase silicon carbide AC to DC converter with a bidirectional functionality. So why is bidirectional of importance? Let's say in the first generation of electric cars, you always took the energy from the grid, used an onboard charger or charging pile to charge the battery in the car, which means there's an infrastructure piece that you only can charge the car if the infrastructure supports the electrical energy, so the electrical energy needs to be available, and then you charge it to the car. So just think about what happens if you have a bidirectional approach. So once your car is not in use, it's parked and connected to a charging pile, the energy provider can kind of remote control your car and charge when there is energy available. At the same time, when there is a lack of control energy, the car and a fleet of cars can be used to support the grid and pump the energy back into the grid. So this is a dramatic improvement of the overall grid infrastructure and grid stability. Another use case here, on the previous slide, we called it vehicle to grid, V2G, vehicle to grid. The other use case is as well V2X, means vehicle to whatever type of other equipment, and the other equipment could be a car. Just think about, you stop by a car, an electric car, with your electric car, somewhere at the highway, this other car ran out of juice, and you can connect the charging cable at your car and the other car and recharge the other car so that it can run to the next charging station. So that's the reason why we see more and more bidirectional use cases. And again, this requires accurate control. This requires super high efficient power technologies like the isolated gate drivers, the monitoring, and obviously the battery management. So I'd like to sum up with these 3 bullet points. So strong electronic system design expertise for the automotive market. That is what TI brings to the stage here. On the analog and embedded processing side, product innovation, including obviously the power management and the sensing products. And last but not least, accurate monitoring and protection not only help engineers increase the system reliability, it is instrumental. It is really one of the key foundations to have reliable, high-powered, efficient EV powertrain systems. Okay. Thank you.